Good morning, good afternoon, good evening, wherever you might be, and welcome to another physics post. This one is called The Walrus and the Carpenter. It is about particle physics. And I should clarify at the outset that I am not a particle physicist, I am an accelerator physicist. And the difference is that the particle physicists analyze the data produced by these machines, and the accelerator physicists build and operate them. It's sort of like applied electrodynamics. We're a lot like engineers. So I spent 20 years in this field, starting with internships and ending up as a postdoc, and then I quit. And this is sort of a picture of how I was feeling and thinking when I quit. So here goes. As an apostate, I view government laboratories as state-funded monasteries, or Oz-like sandboxes in which the creative power of a few minds trained to worship abstraction is imposed on armies of lower-ranking individuals who lack a complete understanding of why they are doing what they do. In the words of Lewis Carroll, "The time has come," the walrus said, "to talk of many things, of shoes and ships and sealing wax, and cabbages and kings, and why the sea is boiling hot, and whether pigs have wings." If I look at a Wikipedia article on big science, or state-funded science, I see an opinion that I agree with. The era of big science has provoked criticism that it undermines the basic principles of the scientific method. Results of experiments which require massive and unique machines like particle accelerators are often difficult to verify. So in this class of big science or cargo cult science, I would classify things such as gravitational waves measurements, neutrino research, most of collider research, complex climate simulations that don't have predictive power. These are all open to a criticism that they are undermining the scientific method. In particular, colliders like the LHC have spent the past 50 years validating a reverse-engineered theory called the Standard Model, and obvious applications of this monolithic Standard Model or of collider technologies are not abundant. These laboratories claim to have spun off internet technologies, but if you take a closer look, you see that really oversells the significance of throwing a log on an already raging fire. Spending billions on a dead-end project with no useful spin-offs could be considered evil, since there are so many needy people in the world and better uses of smart people's time. Like LIGO, the Gravitational Wave Observatory, and the Collider, the LHC, like Neutrino or WIMP research, like Opera, Xenon, and IceCube. These are all operations dedicated to finding a needle in a haystack, and there is an enormous incentive to find a piece of hay that looks like a needle. But these are not the only areas within big science research of questionable utility. The big lasers developed by government-funded science have been used unsuccessfully to try to reach the high temperatures necessary to ignite fusion, and the technology used to build them has been applied to unsuccessful aircraft carrier-mounted laser weapons. Materials scientists plan to use the big lasers to get pictures of materials, and biologists plan to use the big lasers to get pictures of proteins and bacteria. But from what I've seen, the pictures are not that good, and the small science methods used in university labs to get pictures of the same things are often much better and cheaper. I think that the biggest criticism of big science or government-funded science is that once you invest a ton of money in something really expensive, you tend to insist that it is useful even if it isn't. That sort of endemic inefficiency is certainly bad, and it's even evil from a certain perspective. What might be truly evil is the questionable utility. What might be truly evil is the group delusion that takes hold when building and maintaining a large machine of questionable utility. Students and workers train themselves to suspend disbelief and focus on their narrow ant-like roles in the larger project. This narrow focus bypasses the natural skepticism that any good scientist must always have. Thus, an enterprise which purports to train the next generation of scientists ends up training group thinkers who lack big picture perspective. Science isn't about team spirit, but team spirit infects a lot of big science work, and that seems somewhat evil and monolithic to me. Now, I have basically painted the most negative picture possible, and I could focus exclusively on the positive aspects of government-funded research. I could talk about, for example, my husband's effort to distribute an industrial crate standard for better automation and control of industrial systems. I could focus on how these places are often the first work experience young people have, and that it can be a very positive, inspiring experience. But I think that we do everyone a disservice if we only focus on the positive. This is misleading advertising, and you have to go into to build these systems with your eyes wide open and avoid the sorts of pitfalls I've described. So one pitfall I see is complexity. Unnecessary complexity and complexity that obscures the truth. What you see in, for example, CERN's particle detector diagrams are layers and layers of material that take impossible to measure particles and convert them into something measurable. For example, a scintillator takes a high-energy photon and turns it into a lower-energy photon, or a collection of photons which are converted into electrons, which make an electric current that can be sent through some amplifiers and then into an analog digital converter, which will give you some numbers that you can read out on your computer. A question that does not ever get asked in physics circles is a philosophical one. Do impossible to measure things objectively exist? And what are we doing to our students when we teach them to measure impossible to measure things in this way? I think this is a question worth asking, especially since headlines are made every time a group of physicists claims to have measured a new particle or a new property of a particle. Pentaquarks, Higgs, massive neutrinos, WIMPs, oh my. And how many students today are fruitlessly searching for a particle which is dark matter, something that, if you use a different theoretical framework, does not objectively exist. Since these unmeasurable things are also very rare, another question worth asking is, what does it mean to measure something that is buried in noise? Out of millions of collisions per second in a CERN detector, thousands of collisions are tracked, and out of the thousands, only a few are usable for analysis. 1 million to 1 is quite a challenging signal-to-noise ratio. And to parse all of the data that comes out of one of these monster detectors, they start at the outer layer and work their way in. The positions of the measurement devices on the outer layer have to be precisely known with respect to the devices in the inner layers, as does the timing of all of the signals. They match up particles detected on the outer layer with particles detected on the inner layer by using probability statistics, because quantum particles have a lot of intrinsic uncertainty. Many particles make it through the detector unseen, and any data that does not match their model is thrown away. That doesn't sound very scientific. If you throw away the data that doesn't match your model. The outer layer is something like a drift chamber, and it only sees charged particles. The middle layer is full of steel and scintillators, and it is the only component which claims responsibility for converting unmeasurable neutral particles into measurable charged particles. The layer closest to the collision is the Vertex Detector. I have some experience detecting the position of nanocoulomb charge bunches with small antennae, and few micron accuracy is what you can do over a range of a couple of millimeters. Vertex detectors have to detect single charges, and they claim few micron accuracy over a large volume of space surrounding the collision point. In general, what I want to say is that there are many layers with many possibilities to make a mistake in identifying a particle. For example, I learned from an internship doing particle physics, particle identification schemes. A photon is a neutral particle with no charge but also no mass. Really high energy photons might not be detected because they fly right through matter without depositing their energy. That makes any collision for which a photon goes undetected rather worthless, because you need all of the information to reconstruct a collision. Another good example is a pion. It looks almost exactly like an electron, and it is difficult to distinguish the two. Whenever an electron or a pion is misidentified, this will give an incorrect collision reconstruction. And the collisions that are reconstructed in these detectors are so complicated, involving so many different particles, that the idea that a single error makes all of that invalid should worry people a lot more than it does, I think. So in the lingo of particle physicists, one must make a cut in the data of efficiency versus purity. And you see that if you make a perfectly efficient cut, you have practically no collisions to analyze whatsoever. If you make a perfectly pure cut, you will have practically no collisions to look at whatsoever. But if you make an efficient cut, then you may have many, many collisions to look at, but there will always be a certain amount of doubt about each of those collisions, and whether or not they accurately estimate that doubt is a valid question. A CERN scientist might argue, just because it is possible to trick yourself, that doesn't mean that they have done so in their detections of things like the Higgs particle. The standards for establishing the existence of a particle are very high, 5 sigma, the gold standard, as they say. I would ask, what about the Theta Plus pentaquark? By mining noisy old data, it was detected with 5 sigma significance by many labs, yet further investigation showed that all 11 of the detections had been fooling themselves. So if they are fooling themselves about something like the pentaquark, then why aren't they fooling themselves about other, more exotic particles like the Higgs? Behold the story of the pentaquark. When you collide a pair of protons or neutrons, a bunch of smaller particles spill out. These smaller particles exist as pairs of particles which are spinning in opposite directions. They have short lifetimes and they can never exist individually, so they quickly disappear. This is the sort of abstraction that students are encouraged to just accept on faith. Just detach yourself from your intuition and embrace the abstraction. Since these particle pairs seem to come out of the proton and neutron collisions, many scientists decided that meant the protons and neutrons were composed of these smaller particles that only ever exist as pairs and disappear whenever one of the pairs disappears. These scientists then set about figuring out how these particles might be arranged if they existed in a stable form within protons or neutrons. Let's put aside the fact that one cannot directly observe what is inside of a proton or a neutron, and that it is quite a logical leap to assume that the extremely unstable particles that come out of a collision exist in a stable form within the non-collided particles. It is possible that they exist in a completely different form within things like protons or neutrons. But that would be boring for a particle physicist because it isn't a testable hypothesis. Anything you can imagine but can't test somehow doesn't exist in their world, which is, I think, a faulty way to think, because there are always things that we can imagine that don't exist. It's the question of object permanence. Did your mother really disappear when she played peekaboo with you or not? And if you didn't get that lesson and you do particle physics without that lesson, I think you make a lot of mistakes. What particle physicists have done is they go out in search of new testable hypotheses. So they're bored and they get creative. What if these unstable particles exist in a stable form with a more exotic configuration? In a proton, we think that there would be 3 of these unstable particles. But what if there could be 5 of these unstable particles in a stable configuration? That would be a new form of matter called a pentaquark. Very exciting. There's no reason for these things to exist, but if they did, it would be interesting. In 2002, scientists in a Japanese lab, LEPS, looked at their old data and found evidence of a pentaquark, which close to 5 sigma significance, the gold standard of particle physics research. Over the next few years, 11 other laboratories around the world looked back through their old data, and sure enough, they found pentaquarks too. The results ranged from 5 sigma significance up to an even better 8 sigma. But surely 11 laboratories couldn't all be deluding themselves at the same time. Sorry to spoil the party, but they can. By 2008, a scathing review of these results' poor methodology was published, along with several less noisy experiments which looked for the pentaquark and didn't find it. Party's over, as far as I can tell. 11 top physics labs have successfully deluded themselves with 5 sigma significance and crafty data slicing and dicing, searching for a needle in a haystack and finding lots of pieces of hay that looked like needles. This is very disappointing if you're a particle physicist, and embarrassing for the entire community, especially since so many other major results, like the Higgs, are held up as being unimpeachable because of their 5 sigma significance. But I bet you didn't see any headlines about this embarrassment, because big science PR has done a great job of whitewashing over it. This, however, did not stop physicists from whispering about the debacle. To shut down this apostatic whispering, CERN came to the rescue. CERN can save the high-energy physics community's reputation because the more random data you have, the easier it is to increase the significance of a result. And CERN has lots of data. With enough random data, you can always find what you are looking for, if you are generous with how you define noise and creative with how you slice and dice with efficiency versus purity cuts. In 2015, CERN's LHCb found pentaquarks in their data with 9 sigma significance. This either proved that CERN can find whatever it wants within its data, or it proved that the experiments which showed the pentaquark did not exist were wrong. So there were, I don't remember if I mentioned it, but there were experiments showing that the pentaquark could not exist. I suspect that CERN can find whatever it wants in its data, because I wonder what the expected probability of seeing the particle was in their application of Bayes' theorem. It is a bit hard to tell from their article, but Bayesian statistics is a tricky beast. In practical terms, they went through their old data and traced particle paths back until they found a collection of tracks from 5 different quarks that seemed to originate from the same general location. Therefore, there must have been a pentaquark at that location. There must have been a pentaquark? Unicorns are full of pixie dust, and I saw 5 trails of pixie dust leading to a single point. Therefore, there must have been a unicorn which exploded. In my blog post, you might see some technical diagrams of a pentaquark. I know I am being facetious. I'm being a curmudgeon. Maybe pentaquarks actually exist. Maybe unicorns exist. And I'm just being stubbornly skeptical of human error rates in the statistical analysis of large data sets. Maybe I've just become biased after seeing too many stupid people who thought they were smart. Because one thing that a lot of academic institutions do is they basically convince people that they're smart. They train them to be confident as long as they are in line with what their colleagues believe. It's like training group thinkers and overconfident people. Rather than digging deeper into the details of particle physics experimental design, perhaps it is helpful to back up and ask a simpler question. Are there particles with charge but no mass? Is that even possible? Are there any physicists in existence today who still have enough basic intuition to answer a simple question like that without falling back on some groupthink abstraction? What I know is that photons, light, it doesn't have charge, but they are officially without mass within Big Bang standard model physics, whereas they have a little bit of mass within steady-state tired light physics. And when I try to compare the difference between photons and neutrinos, I see that photons have a little bit of rotational motion, but it's non-localized, whereas neutrinos have this small amount of rotational motion, which is a teeny bit more localized than what photons have. I wrote a post on that. I have a post on that later. Z bosons, one of the first things that was discovered by, I think that was in Stanford, Nobel Prize winning discovery. They don't have a charge, but they aren't really particles. They are force mediators, or so-called virtual particles, that pop into and out of existence over an extremely short time scale. When they exist, they borrow energy from the vacuum and temporarily violate conservation of energy. Then you have neutral pions, strange things composed of undefined amounts of different quarks, and no one seems to care that no objects like that exist anywhere other than in the land of fundamental particles. In the standard model, the neutrino is massless, but in the world of neutrino research, a neutrino is a chargeless particle with a tiny bit of mass. In the world of cosmology, the neutrino is whatever you want it to be. Taken all together, you have a zoo of particles that don't objectively exist, but which cause reverse-engineered calculations of noisy Rube Goldberg collisions to deliver somewhat repeatable results for a community that is highly motivated to see what it wants to see. Because you win awards if you see what you're supposed to see. You know, are there sea monkeys in your test tube or not? You can see them if you want to. It used to be that an army of students would be given the data to look at and to decide what was a pion and what was an electron, even though the curves overlap. But now there are algorithms that do that work for them. Yet when you have an algorithm that filters out only the picture that it wants to see, are you not tricking yourself while taking yourself out of the loop? This was certainly the case when a group of PhD students thought they had taken a picture of a black hole by combining terabytes of data from a bunch of different telescopes, so overlaying images until they saw the image they wanted to see. This was also certainly the case when gravitational wave researchers decided that they were looking at the signals of neutron stars colliding. I encourage you to look at those articles. I've written about that as well. There are 3 different articles. Neutrinos are a particularly contentious object because some people think that Pauli made a mistake about spin when he invented the neutrino to carry extra energy away from a neutron decaying into a proton and an electron. A neutrino researcher would protest. Neutrinos have been observed and measured, and Nobel Prizes have been granted for these measurements. A skeptic would reply, that depends on your measurement standards. The first claimed observations of chargeless fundamental particles like neutral pions, Z bosons, and neutrinos happened in bubble chambers, in which charged particles make tracks, but uncharged particles don't. Later experiments automated these sorts of observations by using the large, stretched wire drift chambers and Cherenkov light detector chambers that you see in photos of the LHC detector halls. Massive data sets are broken up and interpreted by armies of students. armed with the assumptions about what they are looking for in the noise. This is a dangerous situation, and these armies of students don't stay at LHC forever. They then go out into the corporate world and apply this same sort of backward reasoning to analyzing big data. So you end up with people who carry the torch of science and say to a corporation, I can tell you what all of this data means. I can be your fortune teller and tell you the way the winds are blowing. Because they've developed this false confidence after working in these particle accelerator laboratories. I think this could be harmless, you just get bad advice, but it could also be dangerous if you get bad advice and act on it to a group's detriment. So experiments or models that attribute actions to invisible entities in large, complex data sets for which multiple self-consistent interpretations are possible should be handled with extreme care. These sorts of measurements end up telling a story based on shadows cast upon the wall of a cave. Someday we may end up seeing alternative explanations of particle mechanics developed more in terms of pilot waves or bubble and fluid dynamics instead of these discrete quantum objects. And I keep an open mind to the possibility that we have made a mistake about spin and neutrinos. But if you say this in polite company today, those physicists will decide that you are a crackpot who thinks that all of particle physics research to date amounts to giving silly names to tiny waves on a noisy ocean which has been stirred up by a chaotic regatta. Actually, I should say not just noisy waves or tiny waves, I should say invisible waves. Waves you can't see. Before consigning me to the crackpot bin, take a close look at some neutrino science from today. Ice cube detects neutrino-induced muons, but there are 1,000,000 times more cosmic ray muons than neutrino-induced muons observed in ice cube. And I am not sure that I buy the story of how they distinguish the two. Opera is another neutrino experiment. They make a muon beam and then block the muons in order to make a neutrino beam. Then they turn a tiny fraction of the neutrinos back into muons to measure the neutrino beam. Gamma rays can also make muons. That's why you have to be careful in such an experiment. This looks like a minefield of errors to me. This was the experiment that claimed that they had measured faster than light neutrinos and then had to retract the claim after finding that it was due to a loose fiber optic cable. Whenever you have two things that can cause the same effect, neutrinos can make muons, gamma rays can make muons. How do you distinguish between the two? They say they can, but I don't think I buy their explanation. This particle zoo gets even more crowded when you consider things called WIMPs, weakly interacting massive particles. All neutrinos are WIMPs, yet not all WIMPs are neutrinos. These weakly interacting massive particles were invented to explain why galaxies appear to be glued together with dark matter that light travels through without interacting. And this is often said without acknowledging that general relativity requires the invention of dark matter because it is a static approximation of a more dynamic system. And if you are creating something that doesn't exist because your theory is a static approximation of a dynamic system, does that something really exist? I don't think so. I don't think it objectively exists, especially if it's something we've never seen before, as in dark matter, matter that light travels right through without interacting. What I know from an internship I took long, long ago is that at Stanford, while working for no pay during maternity leave, Helen Quinn realized that all it takes to glue a galaxy together within standard model of physics and general relativity is to postulate that space is filled with virtually unmeasurable WIMPs called axions. After this, several other physicists copied this idea and came up with their own variation on a virtually unmeasurable WIMP. And then they all started trying to measure them, even though it was clear that their properties made them unmeasurable. This sort of thinking is nothing new in physics. When Pauli couldn't get his math to correspond to reality, he just invented the neutrino, a virtually unmeasurable WIMP, and then all of the numbers worked out. The funny thing about virtually unmeasurable particles is that if people try hard enough to measure them, they start to see them everywhere. It is like looking at sea monkeys through a magnifying glass and seeing evidence that they are playing soccer or playing video games in their parents' basements. If you look hard enough and long enough, you will find the evidence you are looking for. And you may even be measuring something real, but it's possible that you are completely misinterpreting it, that what you're seeing is not caused by sea monkeys, but by something more mundane. This system is fantastic because professors need ever more fool's errands on which to send their students, and inventing more virtually unmeasurable particles for them to measure has been keeping students busy for decades. Neutrinos are the most well-known WIMPs, so why did we need to invent new WIMPs to explain dark matter? It turns out that neutrinos are so lightweight and move so quickly that they would have formed clumps as the universe evolved. So they are a terrible candidate to explain dark matter in a Big Bang universe. The WIMPs that Big Bang physicists are looking for are large, slow, and heavy, yet still invisible and unmeasurable, or rather, virtually unmeasurable. You just have to try hard enough and invest more money in it. After all of this, you might wonder, if you're a curious sort of person, what on earth do WIMPs, like neutrinos and axions, have to do with the Higgs? Since they both fill all of space, shouldn't they be related to one another in some way? As in many physics problems, WIMPs and Higgs turn out to be two incompatible ways to say the exact same thing. The Higgs is like the viscosity that slows down or starts up rotational motion, and mass is defined by rotational and linear motion. WIMP's mass comes from weak rotational plus linear motion, so if a Higgs exists, WIMPs can't exist because coupling to the Higgs field would quickly extinguish them. Likewise, if WIMPs exist, then the Higgs can't exist, because it is stupid to have two incompatible descriptions of the properties of space, one relating to nuclear spin and galactic spin, and the other relating to why all fundamental particles except for WIMPs have mass. If one describes the motion of the whole and the other describes the motion of the stuff around the whole, it is impossible to describe both things in one language. So the solution to this problem that physicists have come up with is that the Higgs and WIMPs can coexist as long as they never see one another. Perhaps this says something about physics culture. Apostates like me can coexist with regular physicists as long as we never see one another. Can we all agree that this story is ridiculous? Instead of talking about WIMPs, Maybe we could instead talk about how to properly apply relativity within astronomy, or about light having a tiny bit of mass. If photons have a tiny bit of mass, will they interact with other photons instead of just traveling past one another in a superposition of states? Does this interaction qualify as a particle? Gamma ray photons interact with one another by producing an electron and a positron, but we've never seen evidence of lower energy photons doing this. Why wouldn't their collisions make smaller, unmeasurable sorts of particles like WIMPs? This would sure solve some problems for tired light cosmology. When I look at all of this, I see that the pieces of the puzzle have been there all along. They just have nobody ever puts them together sensibly. And each compartmentalized part of physics takes their own pieces of the puzzle and tries to put them together and can't make it work. It's frustrating to look at. This story has elements of self-consistency and inconsistency. WIMPs and tired light and the Higgs and Big Bang are two ways to say the same thing. But why do physicists insist on speaking in different languages at the same time? Why do they insist on trying to put two completely different puzzles together? So if you have two puzzles that are similar and then you mix all the pieces together and try to make one puzzle out of that, you're making your job a lot harder. So you have to separate it. To me, it looks like the Tower of Babel fell down when the first nuclear bomb went off, and all of these languages and puzzle pieces got mixed. Now I'll conclude with a word about an experiment called xenon. Although the experiment is trapped beneath a mountain, it is not to be confused with Xenu of Scientology. While xenon is a positively scintillating gas with a very cool name and an amazingly stable reputation, the idea of trying to identify whether evidence of a xenon decay is caused by a virtually unmeasurable WIMP or by some more mundane, measurable phenomenon should cause you to cringe. If it does not cause you to cringe, you are probably a physicist or a data scientist who makes his living by virtually measuring unmeasurable things, things you can't benchmark. Maybe you work for LIGO, the Gravitational Waves Observatory, or maybe you analyze images of black holes, or you measure Higgs particles or pentaquarks, or you search for dark matter. If you don't cringe when you see a picture of an invisible neutrino taken in 1970, which was the first neutrino event, I have a link to that picture in my blog post, there isn't anything I can say that will deter you. Something impossibly cringeworthy is precisely what the xenon collaboration, claimed to have measured with 3.5 tons of xenon gas and a detector array. However, measuring the impossible did not deter the brave Italians in their underground lair at Gran Sasso. Did the air conditioning flip on unexpectedly and cause the detection? Who cares? When funding is threatened, anything is bound to be reported as a measurement. Publish or perish is the name of the game, and nobody in science is going to quit the field of battle with honor. That would be unsportsmanlike. Fight to the death. Laus et gloria. 3.5 tons of xenon gas was not enough. We need 35 tons. 35, yeah. If you made it this far without getting exhausted, you deserve a medal. Maybe you should take a break. I need one. Instead of resting on your laurels, you could go out and buy one of my works of fiction, one of my novels. They're much more fun than this. And relax a bit while I go back over this article and attempt to make it more scholarly and cohesive so that people will trust what I say more. Or you can keep listening. I tried to make the conclusion to this pithy rather than scholarly. Ouch. Sabine Hosenfelder recently published a book called Lost in Math. It laments the overproduction of worthless predictions made by particle theorists, whereas I focused here on the shortcomings of experimental work, which is something I have experience with. She focused on the shortcomings of theoretical work, and while I agree with her conclusions, I don't think she went far enough in her criticism of academic physics. She still has acted as a cheerleader for many big science experiments that appear illegitimate to my eye, and this doesn't surprise me that much because theorists have not been trained to identify bad experimental design, even if they can identify bad theory design. She started out sort of cheerleading for LIGO, and in recent months she's sort of come around to see the weaknesses in their epistemological basis. There are so many degrees of freedom within particle physics models that it is possible to make any number of predictions that could potentially be tested in some very distant ideal future. And when you have thousands of young people who are making large numbers of predictions that are either non-testable or testable in principle only, you end up with a community of people shooting in the dark and calling that theoretical physics. That is one way to be a bad scientist, but there are more. If you fine-tune your theory to match the data, that is also kind of illegitimate. It's reverse engineering. At CERN, they call some of the particle physicists ambulance chasers because whenever there is a rumor of some weird data, 100 young people will jump all over it and try to write a theory that matches it. Looking at some of Dr. Hosenfelder's other blog posts, I am sympathetic with her criticism of the catch-all fudge factor, which is dark matter, and the cloak of legitimacy that the physics journal's demanding style gives to even the worst nonsense. I, however, take a more pessimistic view of that the whole particle physics enterprise maintains its legitimacy based on the sunk cost fallacy and the stylistically high bar to entry into the competition for physics glory. I think it is very sad how many years of life have been poured into this stuff. Exacting style requirements and high bars should be the stuff of the Olympic Games, not science. Thank you for listening to this very long post. I covered all sorts of topics, but I hope that it has provided some food for thought for you and maybe some keywords that you can investigate more deeply. And I encourage you to stay tuned for my next posts. Until then.